Okay, welcome back. What we discussed in the last video in this series was setting up a signal flow graph to represent a two-port S parameter matrix. And we arrived at a graphical picture that looks like what we're looking at here. And what we'd like to do now is continue the discussion by cascading a couple of these two-port S parameters, and at the end of the cascade we'll even just throw in a simple one port S parameter representing perhaps a device under test, and we'll move the discussion along with the goal of coming up with an expression, a single expression for the input S parameter for the entire network. So we'll be able to reduce down the cascade to a single expression involving all the S parameters. And you can do that algebraically. It's very complicated. And what we'll show is you can do it sort of graphically using signal flow graphs. It still ends up being kind of complicated, but perhaps a little less so because you're using graphical techniques. So to represent a second S parameter matrix, we can just drop another copy of the existing one and slide it in next door, and we'll just connect them together. So we have a second S parameter, two-port S parameter matrix represented as a signal flow graph, and we'll cascade them by just like I said, just hooking them up together. And notice, as I mentioned before, we sort of flip-flopped the B2 and A2 waves on the output so that they were at the top and the bottom. And it wasn't absolutely necessary to do that, but as a result, notice that the B2 wave is the output from the first S parameter matrix, and that's going to be equivalent to the input to the second one. So simply by flipping their positions, we can avoid having to have these wires crisscross. When we connect them together, they can just connect directly together. And similarly, the B1 wave is the reflection coming off of the second S parameter matrix, will be the input to the port 2 of the first S parameter matrix. All right. And then, as I said, for our example, I'm going to add in a single, basically a one port that perhaps represents a device under test that we would like to measure. So what we'd like to do is reduce this entire network down to a single expression, so that we can have an equivalent based on all of the different S parameters. And then based on that expression, you can isolate algebraically the desired S11 measurement here that we're looking for. Okay, so let me just hook this up with some connections like we did before, just to make it graphically complete. All right, so here's our overall picture, and what we're going to do is come up with a expression for the whole thing at the input here, so that we can isolate algebraically the effect of this last term, if we so desire. All right, so let's do a little bit of cleanup. What I'll do is quickly make a copy of this and start cleaning things up a little bit. So first of all, what I might do here is start to look at all these A and B waves are kind of redundant in that B2 equals A1 and so forth. What we'll do instead, I'll just start numbering the nodes. Use a different color. So I'll just number them 1, 2, 3, 4. So now B2 equals A1. So that's really the same node. And same down here. And then we've got 5 and 6. And these are shared. So I'll just start to lose these notations for the individual B and A waves. And then the other thing that's going to start to get complicated is that since we have 3 sets of S parameters, keeping them all straight is going to be tough. So I'll just label the first one, I'll add a suffix of, call them A, B, and C. So this is, these are the S21A, and then the second network I'll just label as a B, and the third network I'll just give a C suffix. Okay, so things are looking a little bit cleaner. Let me just do a tiny bit more cleanup, and we'll be ready to look at some rules for how we might reduce this this network. Okay, so I just did a little bit more cleanup, and maybe instead of having this one port hanging off quite so far here, I'll just drag it in a little bit closer. Okay. And so this is what you might see for the example we're looking at if you were reading an app note or some lecture notes on signal flow graphs. It kind of gets reduced down to kind of taking the training wheels off and not showing necessarily the waves that are present at each of the nodes in the first place, or even numbering the nodes as the case may be. And when we start reducing this down, again, I might bring the node numbers back just to help keep things straight. But this is what you would see if you're reading an article, an article about signal flow graphs, a much more streamlined view of the network. And so now we're ready to start reducing this thing, and there's a couple of different sets of rules to do that. The traditional set of rules is Mason's rules, but there's a subset that's much easier to remember, and it's based on Kuhn is the author that has that subset of, it's basically 4 rules that you can apply. It's much easier to remember. And all of this, what I've learned here is based on an article that appeared way back in 1995 in Microwaves and RF. So I'll list a reference to that article. Unfortunately, since it's so old, the PDF isn't really readily available on the internet. But nonetheless, I'll give the information about the article so that you can have a chance to try to look for it using some of the research sites. Okay, so let's go ahead and have a look at these rules. And like I said, there's 4 of them, and then we'll go through the rules, and then in a subsequent video, we'll come back to the example and see how we can apply those rules to reduce the network down. So I'm going to go ahead and just label these, just call them roughly the Coons rules. And like I said, there's 4 of them. A couple of them are really straightforward, and then a couple of them are a little less straightforward. Not hard to remember or anything, but just not super duper intuitive like the first 2 are. So let's say the first one is that if you have a couple of S parameters in series and the arrows are in the same direction, you can combine that into a single branch where the two S parameters are multiplied together. Like that. That seems pretty intuitive. And also equally intuitive, I think, is the second rule, where if you have two branches in parallel, and this is also important, the arrows have to be in the same direction in both cases. In the second case, if they're in parallel, you can replace that with a single branch that is the sum of the two S parameters. Oh, and I wrote S1 twice. I meant to write S2. So the sum of the two S parameters. So that's pretty intuitive. But the part that's less intuitive is that the arrows have to be in the same direction, and having you can't just have an arrow in the opposite direction and call that the negative of an arrow in the same direction. The arrows actually have to be in the same direction. So it's not quite like working with algebra. You're really stuck with the arrows being in the same direction. Okay, so now this one that's a little bit less intuitive, at least at first, but it's very useful nonetheless, is if you have three S parameters. So I'm going to say S1. And then, but one of them forms a loop back unto itself at that node. So it loops around at that node. So S2 and S3. What you can do in that scenario is you can eliminate the loop by dividing all of the inputs to that node by 1 minus the loop gain, or the loop S parameters. So what I'm going to say is this is the same as so there's the output, but instead of the input and the loop, we can combine those together by saying that it's S1 divided by 1 minus S2. And of course, now those two are in series, so you could use the first rule to combine those if you wanted to. But you can get rid of a loop by dividing the inputs by 1 minus the loop gain. All right, so that's a self loop, and that'll become useful. It may not be intuitively useful at first, but we'll see how we can make use of that when we start to go into our example. All right, now the fourth rule involves splitting nodes. Okay, so what that means is as follows. And since this is a graphical technique, it's always most helpful to look at the actual graphical example. So let's say I have a node that is split into three. So I've got S1, S2, S3, and S4. And I'll go ahead and label the nodes here. It's legal with this rule to come up with this kind of an equivalent. S1 where I can actually split this A node into its own branch. And here's S4. And that's legal as long as I make sure to include everything in the path that would have originally been there. So in this case, it's the S1 parameter. I have to add that in, but I can split that off onto its own path. But the output is at E ends up being the same. So now I've got two versions of B. I've sort of split that up into a B prime and a B prime prime, so to speak. It's split off. And so that's the case where you'd have one input and multiple outputs. You can do a scenario of the same rule. Another graphical example is if you have multiple inputs merging into a single output. You can break that apart as well. So let's look at what that would look like. A, B, C, and now I'm going to call that D and E. And so let's say I have S1, S2, S3, and S4. I can rearrange this. Again, having three inputs. S4. S2. If I like, if it benefits me, I can split one of the tracks or one of the paths off onto its own. Again, as long as I reproduce the same S parameters that it would encounter before reaching the final E node. So here again, I've split this into a D prime and a D prime prime, so to speak. Split the D node that way. So these won't necessarily, the rules 1 and 2 are visually and conceptually intuitive. Rules 3 and 4 are a little bit of a head scratcher initially, like how would I use that? And that's where you really need to have an example to see how it would be applied and realize how those two rules could be really quite useful. So in the next video, just to break things up, we'll go ahead and come back to the cascade and see how we can apply these 4 rules to reduce the network down to a single branch graphically. And of course, the expression ends up being quite convoluted and involving all the different S parameters, but it's a process that you can employ graphically, and which is much simpler than trying to do the whole thing algebraically and with matrices and so forth. So ultimately, a useful thing to know, and kind of complicated to learn strictly from trying to read an article. So hopefully these videos help, and maybe you can add this technique to your portfolio. So we'll see you in the next video, and we'll actually get down to the brass tacks, so to speak, of making this all useful. All right, thanks for watching, and be sure to like if you liked it, and leave a comment if you're interested in seeing looking forward to the next video. That, based on feedback, it really helps direct where I should put my effort into which topics as far as continuing the video series and so forth. So thanks again for watching, and we look forward to seeing you in the next one.